All right, so here's the dilemma. We're going to look at some trig limits. So we gotta remember your trig here a little bit. Don't remember trig? Okay, it's been a while. Do we want to do a very, very, very quick trig, just like reminder? Are we okay? I think we're okay. We'll do that later. We're gonna have other needs to. Well, I need to do that later anyway. When we start talking about some other parts of trig. So here's the situation now. We want to try to evaluate. Well, what's our strategy wherever we're trying to take a limit? Okay, plug it in, right? First thing we want to do is we want to attempt direct evaluation, and we'll see if it works, right? And we got three. Before we jump into this, let's just quickly review our strategies. So that scenario, we try direct evaluation, and what happens? It works. We get an answer back that's not weird, right? Then we're done, right? That corresponds to a situation where, remember, where the ant actually would step where he anticipates stepping, and so it makes life easy for us, right? Okay, sometimes that doesn't happen. If that doesn't happen, what if we get an answer that is 0 over 0? What do we call that, first of all? Indeterminate form. And what do we have to do?
We rationalize.
We either rationalize, or we factor, or we do something else. But we've got to do something tricky. We've got to do more work to resolve that indeterminacy. We've got to eliminate the indeterminacy, right? Okay, and then the third case, for now, is actually a pretty easy one. If we attempt direct evaluation, and what's the third possibility?
When you just give up and go.
Okay, yeah, we get some number divided by 0, right? And that tells us, blew up. There's nothing, we just know there's no limit. And we'll get more descriptive here soon, not just immediately after roundup. We'll get more descriptive with that. So what happens here?
No.
This thing.
Bottom equals 0.
Bottom equals 0? What's the, okay, but as x approaches 0, the argument of sine approaches 0. What's the sign of 0?
0.
0. So this is indeterminate, okay? So I want you quickly, and don't get sidetracked, and let's keep this down to a dual rower because we have lots of people in here. Group up with like 2 to 3 other people. So just get kind of, medium-sized groups and figure out, first of all, non-analytically, I want you to just tell me what is the answer to this, and then we'll go look at analytically how we can prove that's the answer, okay? So you got to figure, that's all I'm giving you. You got to tell me what the answer is, not using algebra. So you can cheat. You might, here's a hint, you might want to get out your graphing calculators. Okay. So let's see if I okay, so we want to just go to y equals, and we're going to graph the function, but I have to kind of set this up, and this is important to do. I want to make sure I get my calculator in the proper mode to deal with this issue, and we're trying to graph sine x over x, right? Does it matter in this case if we're in degrees or radians? I mean, I guess technically not, but if it's not specified, where do we always want to be?
Radians.
No, radians, right. And I'm going to talk to you, we'll get into some trig stuff in a little bit, and I want to take that opportunity to just review a little trig and maybe talk to you about, did you talk last year maybe about why radians are, and this is more of a physics thing than a math thing almost, about why radians are inherently better than degrees? Probably did, but it's been a long time. What's that?
More exact.
Okay, well, let me just take a second, and I'm going to review one other quick little topic here on this. There is a real reason why, I mean, have you ever thought about this? Degrees. I mean, how did we come up with degrees? Totally arbitrary. It's a circle, and now we associate a circle with 360 degrees, but 360 is an arbitrary number. We picked it because it's a highly divisible number. That's it, right? So we can break it up. We can conveniently break a circle into quarters and get 90 degrees. So that's useful to us. But that's it. That's really the only reason that we picked degrees. So that doesn't seem right, does it? Doesn't it seem like there must be something invented about degrees that's just not inherently right? Because we could have picked degrees to be 720 in a circle instead of 360. So any answer that depends on degrees automatically just can't be real, can it? I mean, it's totally invented.
Isn't it like the same with pi?
No, it's not. Pi, however, is a real thing. The 2 pi radian measure is a real thing that exists for a reason, and it's fundamental, and it's the same every place. It's just a feature of our universe. And here's how that works. Okay.
But what makes pi real and 360 degrees not?
That's what I'm gonna show you. Okay, here's what makes pi real. If we can make things convenient, but we wouldn't even have to limit ourselves to a unit circle, but a unit circle just makes the math much easier. So let's take a unit circle. I'm gonna be super tricky here. Look at that, wow. Okay. If we take a unit circle, that means the radius is what?
2 pi.
No, the radius of a unit circle is, what does unit mean?
It's like 1.
1. Unitary means 1, right? So a unit circle, by definition, means a circle with a radius of 1, okay? So unit circle, we have radius of 1. What is the circumference of a circle? And this is, would you agree that this is a property of circles? This is not something invented. The radius of, the circumference of a circle is what?
2 pi r.
2 pi r. There's why. Okay? Because if the radius is 1, then 2 pi r becomes 2 pi, right? And so really what a radian is a measure of arc length along the unit circle. Arc length meaning how far has an ant walked along the surface, around the circumference of the circle, right? If he walks all the way around the unit circle, starting there, and goes all the way around, he has walked through the entire circumference, and therefore that is an arc length of 2 pi, okay? If he walks some fraction of that, he's walking a fraction of 2 pi. So let's say he walks through a quarter of the circle. Well, what's that going to be? Yeah, 2 pi divided by 4 is pi over 2, right? So it all makes sense, doesn't it? That's why, because a radian is actually an arc length along the unit circle, it has real meaning. That always correlates to an angle, though, doesn't it? Because even if the circle is bigger than a unit circle, we could say, like, for example, I'll probably never be able to pull this one off, but if I superimpose a bigger circle on top of this one, here, I can move it a little bit. And let's say that we're talking about, and I don't even need a circle. If I'm just talking about an angle, call it theta, well, that angle is always going to subtend some length of arc on the unit circle. So we can always make this correlation between any angle and what would happen if we put the angle at the exact center of a unit circle and correlate that with an arc length along the circle, right? So therefore radians mean something. They're not arbitrary, it's a real thing. And we're gonna do, I've got some of you in physics also. This will come up in calculus too, but more so in physics. A lot of times in physics, we want to break down any kind of motion into 2 different camps. We've got linear motion, which is motion from point A to point B, but then we also have objects, there's internal motion too. Objects can rotate. When objects rotate, that counts as motion also. That's angular motion. And when you want to bring those 2 things together, if you want to, for example, let's just say that we've got this purple disc is like a merry-go-round, and we've got somebody standing out here on the edge of the merry-go-round going around in a circle. Well, if you look down on the merry-go-round, what are you going to see? Let's say the bottom's made of glass. What do you see?
The ground.
Ground's whizzing by. You're definitely moving, right?
Yeah.
Okay. You're moving, but if you want to turn, if we want to know how fast are you moving, we would call that tangential speed. how fast, at this one instant, if you were to let go of the edge of the merry-go-round, you would just fly off tangentially, right? How fast would you be going when you first let go? That's a measure of your tangential speed, okay? How do we relate the tangential speed of this person to their rotational motion? Because rotational motion we would measure in terms of something like radians per second or revolutions per second or something like that. The only way to make that connection is if the angular variables that you're using are in radians. If you try to use degrees, it's not going to work. And it makes sense that it shouldn't work because degrees are made up, right? So whenever you're mixing angular and linear variables, you gotta always use radians. And so really, just to play it safe, why not always just use radians, right? Make sense? Probably, sort of, kind of, maybe, but it will more as we move along. So there's my pitch for radians, why they're so good and degrees are so bad. Not bad, just not as useful. Okay, so let's go ahead and graph this thing. I'm going to put my calculator into radians mode, which it already is, it looks like. And you probably know how to do this better than I do, but we can actually set this thing up conveniently. If I go to, let's put our function in first. It was just sine x over x, right? Okay. So I can go to fraction template, isn't it just alpha f1? So on top, we'll put in sine x. On the bottom, we'll put in x. And for zoom, let's go zoom trig, zoom 7. And we'll look at what that does for us. Okay, there's our function. Now we'll walk along that in a second. But look what this did to the window real quick. If I choose zoom trig, oh, that's not what I expected at all. So never mind. Does yours say negative 6.28? Oh, never mind then. What I was going to say is wrong anyway. So I thought there was something cool about zoom trig, but I guess not. Okay, so here's our function. Now we wanted to know what the limit was as x approaches 0. So what do you suppose is going to happen if I try to evaluate this at 0? So if I say trace 0, enter, what is it going to say? Nothing, because it doesn't exist, right? So I get a blank y value. There's a hole in the function there. But it's pretty clear from the graph what that's trying to be. If I just scoot to the right or the left ever so slightly, what's it at? Yeah, I mean, it's trying to be 1, isn't it? Right? And we're making kind of a guesstimation there, but 1's a pretty nice round number. And so, it makes sense that that's what it's trying to be. And it is, okay? How do we prove that? This is a really cool proof. It's not a very proofy proof. It's kind of a geometry proof, and that's what I like about it. It's very conceptual. It's not, like sometimes proofs can get kind of dry. This is a good one. This is a really good one. Okay, so to get to this proof, I have to show you something first. It's called the sandwich theorem or the squeeze theorem. And it's really simple. Do you have your books? Do we have enough books in here that people could just kind of glance off of a partner's book? If we have enough books, just go to page 62 so I don't have to write this whole thing down. Okay, do we have enough books? Can everybody kind of glance off over somebody's shoulder? Just get where you can share with somebody. Okay, here we go. Right here. I'm going to read through this, and we want to interpret this. I don't want to write it all down, though, so we'll just read it out of the book. So here's the picture that's from the book. This is important. What this says, I need to maybe do one thing here real quick. And this is kind of important, too. It says, if h of x, the blue function here, oh, I want to read this the other way. If f of x, the purple function, is greater than or equal to h of x and less than or equal to g of x for all x in an open interval containing c. So let's stop there for a second. I want you to get to a point where this kind of stuff makes sense to you, and you can read a textbook and read a theorem or a proof and make sense of it, because that is a huge predictor of success in college math. So we want to take opportunities to do this. So what does that mean? Some open interval containing C, this relationship has to hold. Does that mean it has to be that way everywhere?
No.
No. Really what that's saying is just in the neighborhood of x equals C, and that's a word in math, the neighborhood is a word. In the neighborhood of C, meaning in the immediate vicinity, this relationship holds. G is on top, H is on the bottom, F is in between. Okay? Outside of that, other places, we don't care what happens. But in this particular place where we're looking, that behavior is consistent.
How immediate is it?
Well, it depends. Immediate vicinity in this case really just means that an open interval means it could be as narrow as you want it to be, but there's at least one point to the left of this spot when x equals c where that's going to hold.
So plus 1 or minus 1?
I mean 1 point could be infinitely small, but in reality, when you would apply this, say, in a non-mathematical sense, I mean, you probably could have some idea how big that interval needed to be, but it just needs to be enough so that we can see consistent behavior. If I were to move away from this to the right or the left, these lines could cross, and I don't care. I don't care what it does out there or over there. I just want to find some place where on some interval I can define that's bigger than a point, so therefore has an infinite number of points, right? Where it sits on the xy axis, though, I don't know, this could be a 1 and that could be a 2, or that could be a 0.1 and that could be a 0.2, or this could be a 0.00001 and that could be a 0.0002, right? Doesn't matter. We can always focus in more closely, right? Does that make sense? It's arbitrary. There's no threshold because it's mathematical. Anyway, so we've got this situation where we've got this open interval where we've got this ordered behavior of the functions. Red's the biggest, blue's the smallest, F is in between. If it's that way, every place in the vicinity of C, except possibly at C itself. It doesn't matter at C, okay? And you'll see why. What do you suppose we're going to do here if it doesn't matter at C? We're going to take a limit, aren't we? Right? So it doesn't really matter what happens actually at x equals C, but surrounding it, this is the behavior we have. It might still happen at C, but we don't know and we don't care. Then this, and if, I'm going to write these down. If this is true, if the limit, I'm going to write this in red, so it's all nice and color-coded here. If the limit of g of x as x approaches c is some number L, we don't care, just some number, and the limit of h of x as x approaches c also equals L, then what do you suppose that guarantees about the limit of f of x as x approaches c?
Oh.
It's got to be L. Does that make sense?
Yep.
And the reason we call it the squeeze theorem or the sandwich theorem is because the limit of f of x is just squeezed in between those other two limits. If they converge on the same answer, then f has to also, right? Because it's squeezed in between those two for all surrounding values. Make sense? Does the value of f of x actually have to be pinched in between there? No. What if it looked like this? What if we ended up with, what was that?
That was my calculator.
Oh, that was, what if we had something like this? What if the value of f was actually down there? We don't care, because the limit doesn't get there anyway, right? So that's the sandwich theorem or the squeeze theorem. Okay, so now back to our proof. We want to prove that this is the case. Here's how we do it. Let's take a unit circle. Is that kind of flickering?
Yes.
Yeah, a little.
Yeah.
Yeah.
Oh, yeah.
We should have done that.
We should never have mentioned.
Yeah.
How do we do it? Yeah.
Lucas, you guys
Your
have
hand
it.
up there.
Who's Lucas?
Yep.
Lucas, fix it. Sorry.
Maybe just clean the
It's probably not the best. Probably not the best.
Well, Lucas, stand on the desk. There you go.
Okay, so here's our unit circle. Now, we're going to focus in. We got this angle. We'll call the angle theta. Okay, and theta, we use things like thetas and alphas. We use Greek letters for our angular variables, as you probably know. Let's define 3 different triangles here. I want to define a big triangle, well actually 2 triangles and a sector. Okay, so the big triangle looks like this. The big triangle is going to go clear out, and we know that this is a unit circle, so the radius is 1, right? Would you agree that that distance is 1 and that distance is 1 then?
Yeah.
Okay, here's the big triangle. The big triangle is going to come clear out here, and it's going to be a right triangle. Okay? We're going to define a small triangle, which is this isosceles triangle that does that. This is going to be purple. Okay? And we're going to define in between. Would you agree that the green triangle is bigger than the purple triangle?
Yeah.
If you see what I'm doing here, these are just the ends of it. And then here's going to be the in-between sector. So the in-between sector is going to look like that piece of pizza described by that angle.
Oh, that way.
So they both are going along here, all 3 of them.
Oh, I got it.
Make sense? Okay, so they all share this angle. Okay? Orange is in the middle, purple is small, green is big, right?
Yeah.
Okay, let's define those areas. Let's start with the big one. If this is a unit circle, can you tell me what the height of this triangle is? That right triangle, the green one. This can be. We have to define it in terms of theta, don't we? Now, I'll give you a hint here. You want to probably think in terms of SOHCAHTOA relationships. We want to think in terms of right triangle trig. So what we want to do, our strategy here is we want to select the SOHCAHTOA trig function that's going to involve the particular, in this case, the green side and another side that's equal to 1, right? So we have one known side and one unknown side. So what's that going to be? If this is my angle,
No, that's
TOA, tangent, because I've got opposite, the green side would be the opposite side, opposite that angle, correct? And in this case, the base would be the adjacent side. Okay, agreed? So then couldn't we say, we could come up with the trig relationship, yeah, tangent theta equals that distance right there. Let's call it, I don't know, we'll call it x sub g for green equals x sub g over 1, right? So isn't x sub g just equal to tangent theta,
Yeah.
right? Okay, well then I don't even have to write it that way. I'll just write it as tangent theta, right? Make sense?
Yeah.
Okay, that value is equal to tangent theta. So let's write the green area down then. The area of the green triangle is equal to just 1/2 the base times the height, correct? What's the base? Height is tangent theta, so it's just tangent theta over 2? You agree?
Wait, say that.
1/2 times the base times the height. So 1/2 times 1 times tangent theta is just tangent theta over 2.
I thought the height was.
Say it again.
I thought the height was a base.
No, the green. This is the green triangle right here. It's a right triangle. That's the base and that's the height as it currently sits, right? Okay?
So tangent theta over 2, you said?
So tangent theta over 2. Okay? Let's do the purple triangle. We'll take care of the triangles first. The purple triangle now, we don't know the length of this side, do we?
No.
That's unknown to us. We could probably figure it out, but it's going to be hard and it'd be ugly. But ultimately, we just want to know the area of the purple triangle. Well, what's the length of the base of the purple triangle? 1. So all we really need is just the height now, correct? So let's draw in this segment right here. Okay? Now, I want to know the length of that segment, right? Which corresponds to the height of the triangle. Now, to do that, it's convenient for us maybe to look at this smaller right triangle.
Wouldn't it just be one
Okay.
then?
Because, would you agree, the smaller right triangle, I don't know what the base is, it's no longer 1, but the hypotenuse is 1, isn't it?
I was thinking.
So we could, what SOHCAHTOA relationship do we use here then? So there's my angle.
Opposite over hypotenuse.
Okay, what's that?
Side.
Sine. So, right? So we know that sine theta equals opposite, which is, we're going to call x sub p for purple, divided by hypotenuse, which is 1. So x sub p, the height of that triangle, is really just sine theta, isn't it? Right? So I can go backwards then, and I gotta get rid of some things here. I'll rewrite that. Oops. So I could write this distance right here as sine theta, right? And what's the area then of the purple triangle?
Sine theta over 2.
Okay, now the purple triangle is this whole big one, right? It's this,
Yeah.
that's the purple triangle that we're interested in. Height is sine theta, base is 1.
Oh, 1/2?
So 1/2 times 1 times sine theta, so sine theta over 2,
Yeah.
agreed? Okay. So the area of the purple triangle is sine theta over 2. Now the last remaining part of this is just that orange sector, okay? We got to come up with the area of the orange sector. Now, do you have any ideas how we might do that? Okay, we are going to use the radius. The sector, you don't need to know any kind of fancy highfalutin angular math here to find this. You can just do this by thinking of it in terms of a ratio, right? This piece of pizza represents what fraction of the whole piece of pizza?
1/4.
Well, we don't know what the fraction is, but I can come up with it because if that angle is theta, what's the ratio going to be? Theta is the angle that describes our piece of pizza. The entire pizza would be represented by what angle? 2 pi, right? Make sense?
Yeah.
Okay, so would everybody agree here that the ratio of pizza that's left in the box there, that one slice, is just theta divided by 2 pi? Okay, and so therefore it depends on how thick the slice, how big is theta, right?
Where's the theta pizza leftover?
Here's the pizza right here, right? This is our pizza leftover,
Oh, it's not.
and then that's the last piece out of this whole tray,
Oh.
right?
Oh.
Okay. So then the area is going to be the ratio of the ratio of this area, excuse me, of this angle to the whole angle. So theta over 2 pi times what?
3 times 10 over.
Okay, now that we said that this is how much of the pizza is left. This is the fraction that's left. Theta over 2 pi. How would I find out then what's the area of that pizza?
No.
Okay, I'll give you a different question. Let's say that I know that the total.
Would you like find the area of the whole circle?
Yeah, right? Does that make sense? We're taking this fraction of the whole area, right?
Yeah.
Of means times, right? So I've got this fraction times the total area, which is just pi r squared.
Pi r squared.
Yeah, right? Isn't the area of a circle pi r squared? But what's r?
Radius. R is
1. So pi r squared becomes pi, right?
Which is 1.
Would you agree then that the area of this pizza is just pi?
Yeah.
Okay? Times pi. That's equal to the area of the sector, right? Well, the pi's cancel, and I just get theta over 2. Kind of anticlimactic, but that's it, right? So,
I'm confused on the area of the circle.
okay, the area of the circle is just pi r squared, but that equals pi times 1 squared,
Is there?
which is
can
pi.
I be- What about 2 pi hours? Is that the same thing?
Well, okay, 2 pi r, yeah, 2 pi r is the circumference.
Oh,
Right.
Okay.
But what we know here is that we're just trying to find out what fraction of the whole area is represented by this sector. So there's the whole area is pi. We only get to keep theta over 2 pi of that.
Okay.
Right? Does that make sense? Everybody with me?
Yeah.
Okay. So then the area of the sector is
Pi,
theta over 2. Okay? So we all agree on the order of the areas here, right? So we could make this statement then. We could say if we want to put these into a big inequality, we know that the purple area was the smallest, right? So don't want to go smallest to biggest. I don't think it matters. Doesn't really make any difference. We'll go biggest to smallest. We'll do, so we get, this is the biggest area, so tangent theta over 2 is greater than or equal to, right? The middle value, which is theta over 2, which has to be greater than or equal to sine theta over 2, right? Everybody agree? Okay, we good?
And you know that because of the picture.
Because of the picture, right. What if I multiply everything through by 2? That's okay to multiply both sides of an inequality by a positive number, right?
Yeah.
I retain my inequality relationships, so I can essentially just cancel all of those, right? Now, let's take the reciprocal, actually,
Or can we just leave it like that?
Okay, let's do something else instead. I don't want to just multiply by 2. Strike that. What if I multiply each of these things by 2 over theta? Theta is a positive number, right? Based on our picture. Everybody agree?
Yeah.
Okay. Theta is a positive number. So if I multiply by 2 over theta, then I'm getting back the answer. What does this become?
Tan.
That becomes, if I'm multiplying all this stuff by 2 over theta, the 2's cancel, and here I get tangent theta over theta.
Yeah.
Agreed?
So would that just be tangent then? Because with the thetas cancel, or no, because the thetas attached to the tan? I feel like we just made it more confusing. Yeah.
I made it more confusing?
Yeah.
Okay.
You know what I'm saying? Like it just looks more better to do
Oh, you know what I did? Darn it anyway. Okay, I know what I did. I screwed this up. I gotta go back one more time. Hang on. Here's what I wanted to do. I wanted to multiply by 2 over sine theta. That's what I wanted to do. You'll see. Just watch. This will make sense. In hindsight's 2020. You'll see why we did this. I'm gonna multiply everything by 2 over sine theta. What does that do?
Cancel the 2.
Okay, so then this one's gonna become just 1. Agreed?
Yes.
Okay. This one is gonna become theta over sine theta. Everybody agree?
Yes.
Okay. And this one's going to become what?
Tangent theta.
Tangent theta over sine theta, which is just cosine theta, right?
Yeah.
Okay. Right?
Okay.
Agree?
Yeah.
Okay, now let's flip everything. So if I flip an inequality, that's gonna reverse the inequality signs, right? If I take reciprocals of all these. So we're almost there. This is really cool. You gotta hold out. We're almost there. Cosine theta, this becomes sine theta over theta, and this becomes 1. All these get flipped. Okay, now let's take these limits. Let's take the limits of all of these as theta approaches 0. Well, what is cosine of 0? 1. Ah. Okay, so I'm not going to write this down because we're running out of time, but I'm going to take the limit of all parts of this. So I therefore get, because the limit the limit of 1 over cosine theta as theta approaches 0 is 1, right? The limit of 1 is 1, right? So that means what about this limit of sine theta over theta then? The limit of sine theta over theta has to be trapped between 1 and 1, so it converges on 1, right? Because this limit went to 1, this limit went to 1, so that has to get dragged to 1 also by the squeeze theorem. Okay? Does this help? Hang on, hang on. Look back here. If we go back to this, would you agree if we go back to this drawing, if I let theta scrunch down towards 0, would you agree that the purple area and the orange area and the green area all approach the same value? Okay. As that happens, the limit of that ratio has to go to 1. Yes? Well, yeah, we have, you'll see, now we don't do that. Now we got the answer. So we can use that. You know that the limit of sine theta. Yes. Yes.